I'm good now.
Yeah.
My apologies for the technical difficulties. We're just starting the thing. Well, yeah, so the electricity grid in Alaska is a patchwork of microgrids. Even the grid along the rail belt is not connected to Canada, it's not connected to Lower 48. It's its own island. So it's a huge microgrid.
So do you have a DC tie or?
No, not yet. Yeah. Also rural Alaska depends on electricity for their year-round food supply and also health. So that's why Alaska could be more vulnerable to wildfires. Now I can understand. Okay. Yeah. Good. So the FIREWALL project started as a planning grant in 2020. It was right after the catastrophic wildfire event here in the state of Alaska. And we started as a planning grant. It started as a joint project between UAA and George Washington University. And we organized a workshop in summer 2021. We brought together more than 100 participants. And then thanks to NSF, the Navigating the New Arctic program, we were able to transition our effort into this research project that we are working on now. Now, the FIREWALL project is a joint project connecting 4 universities. UAA is the lead, George Washington University, UAF, and Washington State University is also part of this project. Now, our team are doing research on 3 main layers: the built environment, natural environment, and social environment. Maybe now I can hand it over to Katie, because she's the one who is working with other researchers in each layer, and she can definitely better talk about those layers.
Okay.
Yeah.
Cool, thank you.
Yeah.
So yeah, I'm Katie, or Kathleen. I'm a grad student here at UAA. I'm working on my master's in geospatial data science. So it's kind of a mashup of GIS, remote sensing, and computer science. And working in GIS on this project kind of puts me in the middle of all of these pillars, where I'm trying to build different spatial layers that can incorporate all of them. So for the built environment, we're thinking about what's on the ground, what exists, and how can it either start a fire or what's the danger of a fire as to come into contact with it. Natural environment, this is probably where a lot of wildfire science that you've been familiar with is coming from, where fire is starting, what kind of fuel is on the ground, and how can we assess when a fire will occur. Social environment, who's dependent on these built environment components, how close are they to these natural hazards for wildfire, and how can we incorporate all these together? And the end goal of FIREWALL is to have some sort of interactive platform where we can bring different data layers, whether it's a map or social data, together for different stakeholders to look at. So we're thinking about utility managers, wildfire managers, the public, and also maybe healthcare workers that are concerned about those people that are dependent on electricity for their health. So just to reiterate, it's a collaborative effort, and we need to bring multiple perspectives from all those stakeholders that I just mentioned. This past summer, we conducted interviews with people to get an idea about who they're communicating with, where those breakdowns in communication are, so that we can try to improve communication and information sharing between stakeholders, mainly between people that are working, our utility managers, and those that might be concerned with the community access to wildfire. So I'm working on what I'm calling risk assessment for wildfire in communities. So when we're talking about geospatial science, we need to think about scale. That's kind of our first concern. At what scale are we talking about spatially? So when I say community level, I can mean the state of Alaska. So if you've seen a wildfire map for Alaska, this might be familiar, where most of our fires are happening in the interior. But we do have some fire further down and in other areas, and a map like this can tell us kind of where resource allocation is going to be. So because a lot of those fires happen in the interior, the Alaska Fire Service has their major headquarters in Fairbanks, and that's where a lot of their resources are. But it could also, you could zoom in a little bit. This is not in Alaska, this is in Grand Teton. But this is the whole park and trying to evaluate or look at where fire risk is the highest. And so this could also be considered community level as well, right? But then we can zoom in even further. And this is, I think this is somewhere in Spain. But these red dots are buildings, and we're looking at whether these buildings are within a wildland urban interface, which is pretty much an area where wildlands are intermixing with the built environment. And then it's examining the buffers around those houses and how close are they to fuels, vegetative fuels that could put these places in danger of fire. So community level could also mean this, where we're really looking at individual infrastructures, who's living there, how would a fire act in a community like this. So my goal is to be able to make maps like this, where we can look at a community really specifically and determine what the response might be, or inform the response, I should say. But when we do that, we can't really forget these other skills as well. So like I said, how about like the resource allocation statewide, or even within like the borough that this belongs to, where are the resources, how are they distributed? So I just wanted to make a note about the scale, and that we're kind of aiming for this, but we're not forgetting about these other ones as well, and we kind of inform each other. So, risk assessment is kind of it's a little bit of a sticky word, and it can be really nuanced. So I've had to work to kind of figure out what I mean by that. And in the wildfire community, traditionally, we've thought a lot about kind of this red circle here, where we're thinking about fire hazard. So what kind of vegetation is on the ground, the fuels, the fire ignition likelihood, how likely is a fire going to start due to lightning or humans, or maybe a power line. And then how do we expect a fire to behave? That can be dependent on the weather, the wind, or the topography. Fire moves a lot faster when there's a steep slope. So we want to be able to have that in mind, but when we're looking at communities in a wildfire actually coming into the place where people are living and working, moving about, they start thinking about these other things and how that risk it too. So exposure, what kind of people, infrastructure, housing exists on the ground that are in proximity to these fuels or these areas that are more likely to have a fire, or if they were to have a fire. But also vulnerability. So who actually lives in these houses? What are they dependent on as far as electricity or recreation or whatever it might be? And then also the socioeconomic and demographic conditions of the places in this area. So it's a little bit tricky to try to keep all of these in mind at the same time. So sometimes we're kind of jumping between them, but the goal is to be able to have something where we can be in the middle and we can look at them from the perspective of all three of them sometimes. So this is a map that I created. So this is going to be in this red circle, and that's kind of what we're going to spend the rest of this time talking about. I'm going to pass it on to Michael, who's going to share some of his work. But when we're thinking about fire ignition likelihood, I looked into lightning for a little bit, because lightning causes fires that burn the most acreage in Alaska. Humans start the most fires, but those fires don't tend to grow very large. So lightning is definitely really being considered. We do have a lot of it, even though we don't see a lot here in Anchorage. So this is a map, just to give you some context. This is Fairbanks at the top. We're in Anchorage down here, and then this is what we call the valley. And the black line is the real build. So our this is kind of our population center. This is where the most people are living in Alaska. But I looked at lightning strikes that were cloud to ground, so lightning strikes that were actually coming into contact with the ground between two different time periods. We've got 2015 to 18, and then 2019 to 2022. And I wanted to see what was changing. Something that's come up when we talk about climate change in Alaska, that our lightning patterns are changing. Lightning is occurring more frequently and in places where we weren't really seeing it before. So this area up at the top, that's what we consider the interior. So that's where we do see a lot of our fires traditionally. But in the later part of this, we start to see some more lightning happening in this area. So this is something that we can use to start thinking about that resource allocation, or maybe a utility system upgrading some equipment in this area, or maybe doing a little bit more right-of-way clearing, as we see more lightning right there. So my goal here is just to kind of give you a little bit of a view of how I'm beginning to approach the problem. And yeah, I'm gonna pass it on to Michael. He's gonna share. But yeah, we have time for it.
Can I ask it's kind of a multi-pronged question, so it's three questions. One of them is the trees themselves. So I guess over the years, Alaska has become infested with beetles, which have been killing the trees and creating, you know, a huge fuel source. So are you doing anything on that side to mitigate it? That's one question. The other one is, what about controlled burns? Are you doing anything there to kind of, you know, when you see this, you say, okay, maybe if we do controlled burns in certain areas, we can protect, you know, the population center. So that's the second question.
I can't speak much to control burns. I think some do happen. But I can talk about the spruce beetles a little bit. That is something I have been working on recently. So yeah, since 2016, there's been this bark beetle infestation in our spruce trees, and spruce trees kind of range all over here in the valley, and then pretty much up to the Alaska range, which is right here. We haven't, I don't think it's really crossed the Alaska range into the Fairbanks region, but the beetles have left a lot of dead standing spruce, which are like little matchsticks.
Yep. Big match.
But big matchsticks, yeah. And so they're a big fuel hazard, and yeah, there's I've been working on some layers of trying like detecting where they are, but it actually has been changing quite a bit. The infestation is continuing, but some areas like maybe like right here where we've seen a lot of infestation, those trees are now falling down, vegetation's growing back. And so it is kind of this like evolving thing, but there's also new areas of forest that weren't previously infected that are. So I know utility companies are monitoring that closely. They don't want those trees to fall.
So the other question, the last one was that I wanted to ask on the utility side. And I'll speak to Hydro-Quebec, because we had a meeting with Hydro-Quebec a little while ago. They had a huge ice storm last year that knocked out, you know, their infrastructure, their transmission line, and they have no islanding capability to keep, you know, critical resources at least electrified. And they don't have the infrastructure to even build it. But here, when you have the microgrids, you probably have the ability to have, you know what I mean by islanding utilities?
I'm probably gonna pass.
So anyway,
That's something I can help with.
Okay, so it seems like you're set up to do islanding where you can at least keep critical infrastructure power. You know, police, fire, hospital, and that kind of stuff. Emergency response teams.
That's a really good question, because now with grid forming and grid following inverters, definitely with grid forming inverters, we have that capability to keep maybe one or two phases alive. So definitely that can help. And since we have lots of microgrids here in Alaska, so a lot of people now talking about grid forming inverters, I think that's definitely possible.
So I'm just wondering your previous chart, when you talk about the various scales, and you're showing us a community level scale, yes, on the right. Do utility companies use this data also to see how their power lines, if they were gonna get hit, could be located in high fire areas and cause a fire?
So you're asking what kind of data they're using?
Yeah,
I know a little bit, but not much. We've been talking to some utility managers, but I think, yeah, they're concerned with things about like the spruce tree
okay,
stuff of like where the hazardous fuels are and how close they are to their lines because they come up with a plan of how they're gonna do the things. And then, yeah, I think they do have information about who's dependent as far as like how many people and stuff.
You speak up.
Yeah, sorry. She's standing
Yeah,
right here.
yeah. Making your private
But yeah, I don't
conversation.
know if you have anything to add to that.
Yes.
Yeah.
Do you think the spruce beetles, their infestation actually exacerbated the lightning piece? Maybe the lightning is consistent over the years, but it wasn't as dangerous as it is now with a lot of dead, matchsticks there. I'm just curious, is it really the spruce beetles that you need to worry about and not necessarily the lightning itself?
Yeah, so yeah, they're both things to worry about. My spruce beetle maps just aren't, I'm not presenting them, but I have been working on that a little bit, so, but yeah, when I'm looking at something like this where I'm thinking about, so those both lie in this red circle, right? So the hazard is the fuel on the ground and the ignition likelihood is due to lightning. So we want to be able to look at those together. Where is it likely that lightning's going to strike and maybe start a fire?
Yeah.
But then how is that fire going to act there?
So I mean, Carol can speak to this too, but in reliability, we do this analysis called FMEA, failure mode and effects analysis. And maybe the effect is because of the spruce beetle, not the lightning. So you got to do that whole tree and decide what's the overlay. How does it sit in there? And maybe the real answer is control of the spruce beetles would control a lot of this red area.
Right. Yeah, and I think
I don't know. I'm just suggesting.
Yeah, no, I think that's a good point. Yeah, like, we can't really control the lightning, but we control the forest to a degree of depending on where it is. I think our goal is to just provide the information so that those decisions can be made. I'm not gonna go out there, we're not going out there with chainsaws, but we need to help people decide do you have that capability to decide.
So for example, in the Quebec thing that I mentioned, Quebec doesn't do anything to handle control burns or even put the fires out when they start. They just let them burn.
Right, and we actually do that quite a bit here as well. But depending on where the fire starts, but yeah, I'm gonna pass it on to Michael for the.
So,
some other question, but yeah.
one last question here
Yeah.
about the power lines. So it's not really clear to me. You put power lines in that category of fire ignition likelihood. By what mechanisms do the power lines ignite fire? Is it when a tree falls on the power line and causes a spark, which ignites the fire? Or is it when a power line gets hit by lightning, or is it both? Or is there some other mechanism that causes power lines to be at the cause for fire ignition?
I'm thinking both for that.
Yeah.
This list traditionally is people are thinking about lightning and humans. I added power lines because it's relevant to what our group is interested in. So I'd say that this list here, it's a short list, just to kind of express the idea of what I mean by hazard, what I mean by ignition likelihood, but we could probably spend all day adding to that.
Okay,
So
okay.
don't take that as an exclusive list, so yeah.
Nolan had a question?
Oh, yeah.
Yeah, just all those matchsticks makes you wonder if we did cut them down, turn them into firewood, what was sort of, how long would that last? Anyone talk
I mean, a
about
lot
this?
of that dead standing spruce is not necessarily within our communities. People do mitigate that around their houses quite a bit. So some of those areas where that dead standing spruce is, now that it's been a number of years, they are falling down on their own and the fire hazard is decreasing in those areas. So in my opinion, I think it's a lot of work to pull that out and use it as firewood because they're often not like right on a road. Is a big component in Alaska.
Yeah, I live in Colorado and we have a huge issue with that too, but a couple of years ahead of you guys because we were further south where it started. And the state of Colorado has actually tried to be proactive in cutting down and bringing down those trees before they fell on their own and cutting them and burning them. But there's been a conversation around the release of carbon dioxide in the atmosphere and the exacerbation of global warming by the energy used to try to treat the problem mechanically and by fire. So it has pros and cons. So it's interesting to know that you're letting the trees fall down and you're actually seeing a decrease in fire hazard by using that approach. Because other areas have tried other things, so, yeah.
Yeah, I mean, a lot of these trees are in areas that if they were to catch on fire, we might let them burn to a degree before they enter.
Can you talk a little bit about the data? I'm guessing the data is generated by a lot of different entities. And other entities want to get access to it. So how do you store and manage and share it?
You mean for as like the firewall group or just me? What
Yeah, I mean, if there's matchstick to whatever, you know, how was the distribution is? Maybe you're generating your data and somebody else wants to see your data so they can leverage it for something else. What kind of platform do you use for that?
I think that's something we're still thinking about. But as far as what, right now we're pretty early on where I think we're generating data and making layers and thinking about how they want to look. We're still just speaking with stakeholders to figure out what they need and what they want to see. But yeah, I don't know if Mohammad has anything to add to that, but
I would think different stakeholders probably want to share that data.
yeah, there's some things that they don't share. So yeah, we're trying to figure out what does somebody have that somebody else wants and to be helpful and bridge those gaps. But as far as like specifics about that platform, I don't particularly there yet.
Nice start. I also, I'm Michael Lindemann. I'm a grad student, EE grad student here working on the firewall project and also on some other projects. I did want to touch base on something you asked earlier about islanding capability. One thing sort of interesting from an EE perspective is that most power plants here in Alaska are built with the black start capability. So that's not something you see in the States much. Mainly that's because Alaska is, as most people know, an earthquake zone. And so if we have a major earthquake, basically all the power plant is going to shut down mode. Well, that means they all have black start capability. So that we can very quickly start up from an earthquake, or if there was an event where we needed to shut down a transmission line on the rail belt, it makes it very easy for us to island in a power plant to come back up online. So it's something sort of interesting that you don't see most places before. So anyways, on the firewall project, I have been working on doing wildfire prediction using low resolution Landsat imagery. Most people in the room have probably heard of Landsat. It's been around since 70s or 80s, very long time. The problem with Landsat is that each pixel of a Landsat image is 30 meters, right? So you're thinking about a 30 meter by 30 meter square. And that's extremely low resolution. Now some of the commercial satellite capabilities, you can get like, what is it, like 6-inch resolution or something from some of these satellite providers that are out there now, depending on how much you want to pay. And the other thing that I always joke about on this is that here in Alaska, like I say, we use Landsat because it's what we have available. The other satellites that are available that we don't have access to are, satellites that cross over Alaska also cross over Russia. I'll just say that. So there are definitely satellites that are very high resolution, but we don't have access to them. So I've been using these Landsat images to develop machine learning models to sort of forecast where we think we might see wildfires in the future. What I started with was a data set put out by the Canadian government. And the main thing with any of these machine learning models is having a labeled data set to start from and work with, right? That's where you spend a very large portion of your time. So luckily, the Canadian government had put out basically a data set of about 43,000 images, half of which were labeled wildfire, and half of them were labeled no wildfire. And so these pixels had all been downsampled to 350 pixels by 350 pixels. The key, though, is that these images were generated from the Canadian government didn't say what satellite they used, but it was definitely higher resolution than Landsat, a much better sensor, basically. And so when I say medium to high resolution, that's what I mean is that the on-ground resolution is much higher than Landsat. And so what I always tell people on these slides is if you keep your eye on these images, we will now look at what I was able to generate from Landsat images. So keep your eye, boom, there's the Alaskan images. So we'll flip back and forth between those really quick, and you can see the major difference with the Alaskan images. And so, as you can imagine, pulling data out from these sort of images, which admittedly on the projector, they look even worse than they are, but I assure you that's definitely about what they look like, is much more difficult than pulling data out from those super great images that we have from Canada. So the issue here is that if you train a model on the Canadian images and then you try to apply it to the Alaskan images, it does not work very well, right? Because for a multitude of factors. One of them being that the Canadian images were generated from a region that doesn't have the same sort of vegetation that we have. Also in the Canadian images, they didn't have, giant mountains and stuff. Alaska is very interesting that we have a lot of these areas where the forest comes right up to the mountain and then it's just like rock, right? So a model seeing that, you got to think of it as like a small child, right? It's going to be like, oh, I have no idea, that doesn't understand, basically, it gets lost. And so this is what's called a people component analysis. And so this allows you to really look at the difference between the Canadian images and the Alaskan images. So if we look here, you can see the Canadian images have a nice spread, right? They're the ones in the background, the red and the blue there. The Alaskan images, by contrast, are basically smashed right on top of each other. And so this really tells you why, one of the reasons why the models have a really hard time doing well on the Alaskan data is that, the Alaskan data is sort of just, it has no idea what it's looking at that point, right? So we tried some pre-trained models on this data, as I mentioned before, and so we were seeing like a 50 to 60% accuracy on the Alaskan data versus like 96% on the Canadian, right? And we basically tried logistic regression, MLP, and custom CNNs, because those are the sort of the models you always hit if you're trying to do machine learning stuff to just get an assessment as far as how well these models are going to work, right? Overall, I believe the best accuracy we saw was on the Canadian data, at least, was this 98% with a custom CNN that I built. So this is an example, or well, this is that custom CNN basically, and as we say, 98.4. I believe since this has happened, I have gotten up to around 99% accuracy in the Canadian data, which is actually very impressive. Still, no matter what, they basically all did terrible on the Alaskan data, as you can see, around an accuracy of about 75%, which is really not useful, right? Like if you're getting 75% on all your exams, you're basically just scraping by, right? So this really was not something that we could move forward with at that point. So what we did, it's called a teacher-student model fusion, and basically what this is we train up a model on the Canadian data set. But we actually use that to, you can almost think of it like a grandparent model on the Canadian data set. And then it has its children models, right, on some of the Alaskan data, right? And then it has basically two children. Then those two children are specialized on the wildfire and the no wildfire on the Alaskan data on a very, very small subsample, right? And then we do what's called a model fusion. And we bring them together into one model. And then that one model then does predictions on the rest of the Alaskan data to see how it performs. What's really cool about this is that these convolutional neural networks are sort of like a brain, right? They're a neural net. And so we're able to basically pass down stuff from the grandparents to the children, basically. If you want to think about it like that. And so we're doing that, we were able to actually get much better. Sorry, this is the pseudocode, by the way. I left this in case anybody wanted to see it, but this is the pseudocode for basically what we were just looking at there. If anybody wants to talk about it, definitely feel free. We can talk about it later. It's super cool. So doing that though, if you guys notice now, we got up to an accuracy of almost 90% on the Alaskan data using this teacher-student model fusion, where we basically pass down the qualities from the grandparent models. And so one thing that I found was really interesting on this is if you look at this bottom chart here, we tried originally, remember that CNN that I was saying that got 98% accuracy? We originally tried to use that as like the grandparent model, right? And if you look at down here, the accuracy was 81%. So what that really boils down to is that because that CNN did so well on the Canadian data, it actually had biases, just like we can introduce biases to our children and biases to people around us, right? it was too biased on the Canadian data. And so what we found was that if we had a model that was not as good on the Canadian data, it actually did better overall in the end. And so that took a little bit of trial and error to figure out. Found that really fascinating. But in the end, like I say, we are currently at about almost 90% accuracy on the Alaskan data, and we're really hoping to bump that up some more. I have since then been working on some other stuff, but we're hoping to move back to this summer and get some more results. So looking at the model, you can see that we have this 44 here is something we don't want to see, right? So what we should see is basically these numbers on the cross here is the confusion matrix. I mean, most people have seen them. Ideally, this would be 0, and then that would be 0 if the model was working perfectly. But basically, the model here is predicting no wildfire when it really should be a wildfire image, right? Like it should be predicting wildfire, and it's predicting no wildfire. So basically, it's like a false negative that it's predicting. So where do we want to go from here? So currently, that model only uses the RG and B bands of the red, green, and blue bands of Landsat. Landsat has more than the RG and B bands. It has some infrared bands and stuff like that. So we are hoping to use infrared. And so here is an example of if you actually use some of the infrared stuff and you calculate the NDVI. And so this is pre-fire, and then you can see post-fire, we see this big scar. So our hope is that we can do this sort of thing, and we can have the model start to pick up on some of these, maybe some inherent traits from before the fire, so that we can do like fire forecasting essentially. Hopefully it can start to learn on some of this other stuff. So as far as future work, we're going to start integrating like the model that I've done, the model that Katie has done, and all these other stuff into an app for the Firewall project, right? So an all-inclusive, cohesive environment that our utilities can put their data and their information into, and the app can hopefully, and in the end, you know, give them how do I put it? Give them ideas or give them pointers to be like, hey, we think that the wildfire risk in this area is getting pretty high. You might want to start to pre-stage some assets, because in Alaska, one of the main issues we run into with responding to these fires is getting stuff out there, right? Because Alaska is so huge, we have a really hard time moping or, you know, getting your stuff out into these areas. So if they can pre-stage some assets in these areas, that would be huge, so they can start to contain these fires. And also they might be able to start doing fire breaks before a fire even happens, right? If we're like, hey, you know, we're seeing a really huge fire risk in this area, they can go in and do a fire break before anything has even occurred at that point. The other thing with this app is we hope to be able, if you can see the grid portion here. So we hope to be able to have the app tell them, hey, we think you might want to put a second feeder in this area or something like that. So that way they can feed it an area that's at higher risk more of the time. Maybe they'll do a second feeder, so that way if a wildfire comes in, impacts the one feeder, they can always feed it from the other side, basically. Give them redundancy and that sort of thing. So thank you.